Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So this is part 14. So on distributed forces, and we apply hydrostatic uh, pressure principle as well as the principle on buoyancy by Archimedes. And this part will end up to part 15. So the theory behind hydrostatic pressure as well as for buoyancy laws were already presented in the preceding videos. So I hope that you can continue with the applications of those principles in the following problems to follow, and hope you can follow also the explanation and the solutions. Level 71. The cross-section of a concrete dam is as shown. For a 1 meter wide dam section, determine letter A, the resultant of the reaction forces exerted by the ground on the base AB of the dam. Letter B, the point of application of the resultant of part A. And letter C, the resultant of the pressure forces exerted by the water on the face BC of the dam. Density of concrete 2,400 kilograms per cubic meter. And this is the dam cross-section. Let's consider 1 meter wide dam or 1 meter perpendicular to the paper or to the screen. Let's divide the dam into the following parts because this is mentioned parabolic and this is the vertex. So for concrete dam, let's divide that in that manner. We have parabolic section and rectangular section. The pressure distribution on the vertical projection of this face is triangular, 0, top, pressure at the bottom 9.81 times 3, or specific weight of water times 3. So that's F, and this is 1/3 of 3, so 1 meter. And this is weight of water, which is represented by the weight of water inside the parabolic section. So this distance is 3/8. So remember centroid formula, 3/8 of 2. 3/8 of 2 is 3/4 or 0.75 as shown. Then we have weight 2, and this distance is 1/4 of 2, so 0.5. And of course weight 3, concrete, this is half of 1.5, 0.75 meter as shown. So this is Ry, Rx to the right, and Rx is just F, and the distance of the resultant on the foundation where it crosses the base from A is denoted by X sub A as shown. So this pressure is specific weight of water 9.1 times 3. So therefore F is volume 1/2 of 9.81 times 3, base height 3, perpendicular to the board 1. So 1/2 base 9.81 times 3, height 3 meters, then perpendicular to the board 1 meter, so 44.145 kilonewtons. For weight 1, it is specific weight of water times volume of water. Volume of water is area of parabola, which is 2/3 base times height, 2/3 of 2 times 3, and width perpendicular to the board 1. So weight 1 is 9.81, quantity 2/3 of 2 times 3 times 1, so 39.24 kilonewtons. Weight 2 is concrete, so specific weight of concrete is specific gravity of concrete times 9.81 specific weight of water times volume of concrete, which is area of spandrel times 1. Area of spandrel of parabola is 1/3 base times height, so 1/3 of 2 times 3, then perpendicular to the board 1. The specific gravity of concrete is 2,400 divided by 1,000 kilogram per cubic meter density of water, so 2.4. So the specific weight of concrete is 2.4 times 9.81. So weight 2 is 2.4 times 9.81. Volume 1/3 of 2 times 3, then perpendicular to the board 1. So 47.088 kilonewtons. Weight 3 is 2.4 times 9.81, then volume is 1.5 times 4 times 1. And it is 141.26 kilonewtons. Therefore, F is Rx, Rx is F, and F is 44.141. So that's the resultant reaction force, X, 44.14 kilonewtons rightward, while Ry is sum of weights. Ry is 39.24 plus 47.088 plus 141.26. So R sub Y is equal to 227.6 kilonewtons upward. That's the resultant reaction at the base. But the resultant vertical force is downward. And let's use Varignon's theorem here to solve for XA. So Ry times XA, which is clockwise, equals clockwise moments of the components minus counterclockwise moment of the component, which is F. So F will be treated negative here. The moment of F about A is treated negative. So 227.6 times XA equals weight 1, 39.24 times 2.75. 1.5 plus 2 is 3.5 minus 0.75 is 2.75. So the moment arm of weight 1 from A is 2.75. So that's 2.75 plus weight 2, which is 47.088 times 2 meters. 1.5 plus 0.5 is 2 meters. So 47.088 times 2, then plus weight 3, 141.26 times 0.75, then minus F, minus 44.145 times 1. So solving for XA, XA is equal to 1.159 meters. So the resultant crosses the base of the dam 1.159 meters to the right of A. Then letter C, the resultant of the pressure forces exerted by the water on the face BC, and it consists only of F and W1. So the magnitude is square root of F square plus W1 square. So RBC, square root of F 44.14 square plus W1 39.24 square. So RBC is equal to 59.06 kilonewtons, and it is directed down to the left. Tangent theta is W1 over F, or vertical over horizontal, and that's theta. So tangent theta equals 39.24 over 44.14. So theta equals 41.64 degrees. Therefore, the angle that the resultant force on the face of the dam BC makes with the positive x-axis is 180 degrees plus theta. 180 plus 41.64 is 221.64 degrees, or 221.6 degrees. So theta x is 221.6 degrees, and that is understood counterclockwise from the positive x-axis to that direction. Level 72, the dam for a lake is designed to withstand the additional force caused by silt that has settled on the lake bottom. Assuming that the silt is equivalent to a liquid of density rho sub s equals 1760 kg per cubic meter, so the specific gravity is 1.76, 1760 over 1000 for that of water, so 1.76. And considering a 1 meter wide section of dam, determine the percentage increase in the force acting on the dam face for a silt accumulation of depth 2 meters. The density of concrete is 2,400 kilogram per cubic meter, or the specific gravity is 2.4. So this is the figure. So if the depth or thickness of silt is 2 meters, so the water portion is 6.6 minus 2, so 4.6 meters. But originally, there was no silt, so the increase in the force acting on the dam would be the increase in the horizontal force. Uh, the original force is due to water only of depth 6.6, and the final force would be due to this water and due to this silt. So for the solution, pressure distribution when only water is present would be this. The pressure at the bottom is 9.81 times 6.6 rather. And let's call that F. And there's no need to level this distance 6.6 over 3 because we don't need that, just the increase in force. So this is the original force, which is equal to the volume of this pressure diagram. And this is the pressure diagram with the silt, 9.81 times 4.6, where 4.6 is 6.6 minus thickness of silt, which is 2. And we have to transmit the pressure, and we have another pressure here, which is 1.76 times 9.81 times 2 meters, the thickness. So again, this is 1.76 times 9.81 times 2. So we compute the volume of this pressure diagram and add, that's the total horizontal force on the face of the dam when the silt is accumulating at a thickness of 2 meters. So call that F1, F2, then for this triangular pressure diagram, F3. So remember, that's 2 meters, so F3. So F is volume, 1/2 of 9.81 times 6.6 times 6.6 times perpendicular to the board, 1 meter. So 213.66 kilonewtons. F1 is 1/2 of 9.81 times 4.6 times 4.6 times 1. And it is 103.79 kilonewtons. F2 is simply 9.81 times 4.6 times 2 times 1. So area of the rectangle times 1. 9.81 times 4.6 times 2, so that's the area of the rectangle, times 1, so that makes it volume, 90.25 kilonewtons. Then finally, F3 is 1/2 of quantity 1.76 times 9.81 times 2 times height 2 times perpendicular to the board 1, so 34.56 kilonewtons. So percentage increase in the force is 100% times quantity F1 plus F2 plus F3 minus F divided by F. So F with silt present, 103.79 plus 90.25 plus 34.53. So the force when there is an accumulated silt of 2 meters thick is 228.57 kilonewtons. So percent increase in F is 100 times 228.57 minus 213.66 divided by 213.66. So from there, we can solve the percentage increase in force equal to 6.978%. Level 73. The base of a dam for a lake is designed to resist up to 120% of the horizontal force of the water. After construction, it is found that silt that is equivalent to a liquid density of 1760 kg per cubic meter is settling on the lake bottom at the rate of 13.54 mm per year. Considering a 1 meter wide section of dam, determine the number of years of service until the dam becomes unsafe. So the dam becomes unsafe if the silt accumulates to a depth of h. as shown in the figure. And that H is computed by equating the force, increase in force with the presence of silt to 120% or 1.2 of the force when there is only water present in this vertical face of the dam. So for the solution, this is the pressure distribution when only water is present. So this is 9.81 times 6. Let's call the thickness of silt as H. So call that F. And this is the pressure distribution with water alone. So since we do not know this is H. So this height or depth of water is 6.6 minus H. So the pressure here is 9.81 times quantity 6.6 minus H. So the height is 6.6 minus H also. Then by Pascal's law, you have to transmit the pressure. So rectangular, then we have pressure diagram here, which is triangular. And this is equal to specific weight of silt 1.76 times 9.81 times thickness of silt, which is H. So 1.76 times 9.81 times the thickness of silt H. So call that F1, this one for equivalent rectangular pressure diagram F2, and for this triangular in the silt portion F3. So that's H and that's F3. So F is volume, 1 half of 9.81, 6.6 times 6.6 times 1, so 213.66 kilonewtons. So with the presence of silt, the force should be 1.2 of 213.66. So 1.2 of 213.66 is equal to 256.39 kilonewtons. And the components of Fs would be F1, F2, and F3, which are in terms of H, functions of H, the thickness of the silt, and we equate it to this, then hopefully solve for H. So F1 is equal to 1 half of 9.81 times quantity 6.6 minus H times height 6.6 minus H perpendicular to the board 1. Simplifying 4.905 times quantity 6.6 minus H square. F2 is 9.81 times quantity 6.6 minus H times height H times perpendicular to the board 1, simplifying 9.81 H times 6.6 minus H. And F3 is volume of this pressure diagram. So 1 half of quantity 1.76 times 9.81 times H times 1 perpendicular to the screen or board, 8.6328 H square. So adding F1, F2, and F3 and equate it to 256.39. So 4.905 quantity 6.6 minus H square plus 9.81 H times quantity 6.6 minus H plus 8.6328 H square equals 256.39. If we simplify this, it leads to quadratic equation, then hopefully solve for H. But with the high-tech calculator, we can solve for H directly, and H is 3.3856 meters or 3.3856 meters. So that's the thickness of the silt, such that beyond that it will no longer be safe. And we equate it to the constant rate of silt accumulation, which is 13.54 mm per year or 0.01354 meter per year. And therefore, we can solve for y in years. Y therefore is equal to 250.0 years.
Level 74 problem. An automatic valve consists of a 225 by 225 square plate, 225 by 225 mm square plate that is pivoted about the horizontal axis through A. If the valve is to open when the depth of water is D 450 mm, determine the distance H from the bottom of the valve to the pivot A. So here is the given situation. The depth is 450 mm at that situation. And this is the pressure diagram. So when the depth is 250, that means the distance from water surface to the top of the square gate is 450 minus 225, so 225. So the pressure here is specific weight times, we don't need to convert 225 mm to meter. We just use consistently mm so that the resulting value of H would also be in mm. So the pressure at the bottom is equal to gamma of water times 450 or 0.45, but I'll just use 450 mm, so that answer will be in mm. So here it's gamma times 225 mm. And let's divide this trapezoidal pressure diagram. This is not included because this pressure acts on this uh, body. This may be a wall of another body, so it does not contribute to the force on this square gate. So let's divide this into two parts. Let's call this F1, and the distance of F1 from the top is 1/3 of 225 or 75 mm. F2 for this pressure diagram, triangular pressure diagram, its distance from the bottom is 1/3 of 225 is 75. And the force F, the resultant of F1 and F2, must be just above A so that it will open the gate. So when F is just above A, then it will open. So when we say just above, it means that F just passes through above A and its moment is 0. And the moment of the resultant F about A is 0, it is also the sum of the moments of its components. One is clockwise, the other is counterclockwise. So they have opposite, these moments of F1 and F2 have opposite senses. So that's it. Then this is again 1/3 of 225, 75. F1 is also 75 from the top. Then the distance or moment arm of F1 from A is, because this is H in terms of H, this is H minus 75. Then this moment arm is 225 minus 75 is 150 mm from the bottom, and because this is already H, so this moment arm is 150 mm minus H as shown. So F1, F times 0 equals F1 times quantity 150 minus H, then clockwise positive, then minus F2 times H minus 75, where F1 is equal to the volume of the pressure diagram, 1/2 of 225 gamma, or F1 times 150 minus H equals F2 times H minus 75. So F1 is 1/2 of 225 gamma times 225 height times perpendicular to the board 225 also. So again, 1/2 of base times height, 1/2 of gamma times 225, which is this. Height is 225, then perpendicular to the board because the gate is, or the valve is square, 225 by 225, so times 225. So it is 225 cube gamma over 2. Then F2 is also volume of this pressure diagram, 1/2 of 450 gamma times height 225 perpendicular to the board 225. So simplifying, that's 225 cube gamma. Substitute into this equation, 225 cube gamma over 2 times 150 minus H equals 225 cube gamma times H minus 75. Cancel out 225 cube and gamma, then cross multiply, 150 minus H equals 2H minus 150. 2 times H, 2H, then 2 times negative 75, negative 150. 300 equals 3h, so h equals 100. So that's the answer to this problem. Level 75. The 3 meter by 4 meter side of an open tank is hinged at its bottom A, and is held in place by a thin rod BC. The tank is to be filled with glycerin with a density of 1263 kg per cubic meter. So determine the force T in the rod and the reaction at the hinge after the tank is filled to a depth of 2.9 meters. So here is the given situation. The pressure diagram is again triangular, and the pressure at the bottom is specific weight of glycerin, which is, if the density is 1263, then divide by 1000, 1.263 times 9.81. So the pressure at the bottom, that's the pressure diagram, 1.263 specific gravity times specific weight of water times depth. D is 2.9 as mentioned here. So that's the pressure in kilopascals, 35.931 kilopascals. And the force, equivalent force, is the volume of this pressure diagram. Remember, this is 3 meters, so perpendicular to the screen or the paper, 4 meters. So that's his F. Then its distance from the bottom is 1/3 of 2.9, 2.9 over 3. And these are the reactions AX, AY at A. So let's solve for F. F is volume of pressure diagram, 1/2 of 35.931 kilopascals times 2.9 meters, the depth, and perpendicular to the board, 4 meters. So 208.4 kilonewtons. Then we sum up moments about A equals 0. So T times 3 equals F times 2.9 over 3. From there, we can solve for the tension, which is equal to 67.15 kilonewtons leftward. And summation forces X, AY is 0, summation forces Y, all forces are horizontal. Then summation forces X 0, 208.4 minus T 67.15 minus AX equals 0. So AX is leftward, and it is equal to 141.2 kilonewtons. So that's it for this problem.